All right, so beginning chapter 15 on the topic of the sun. This is one of two chapters that covers the sun. The focus here is on observations of the sun and the way it affects the solar system as a whole, with its light, sure, but also with its solar wind, which we've briefly talked about before. This is in contrast to chapter 16, which delves into the interior of the sun, both in the sense of talking about the processes and layers that go on inside of the sun, but also the fundamental physics of fusion, which is the energy source of the sun, as well as all stars. And a big idea, big topic. Couldn't stress the importance more of the idea of fusion energy, which is a form of nuclear energy. So before we get to all that, let's talk about the composition of the sun. So what elements, molecules is it made out of? Why do we study the sun? Well, as I was talking about before we got into our lecture, it's close. So it is the closest star to us, and thus we can make lots of good measurements. Okay? And the other side of that answer is that it affects us, right? We want to make sure that we understand the sun for making sure we understand solar weather. Have you heard about like solar storms? Good to be able to predict them. It's good to know about the potential effects of solar storms. In general, solar storms aren't something that you have to worry about in your day-to-day life. They're not going to, cause mass destruction or displacement of humans or, anything like that. But they do matter for certain technical aspects. They certainly matter as we travel more into space and for people on the space station, for example. So back to the composition. So the atomic composition, so just looking at the elements that compose the sun in terms of percentage of atoms, it's 92% hydrogen. That is the element that dominates the sun, just as it dominates the solar system, the entire universe. Most of the universe is hydrogen, okay? And what's cool, and it's like I've been waiting for this for so long. I love talking about the solar system, but so much of physics is based off on the physics of stars, but so much of astronomy is based off of what stars do. Stars play this fundamental role in explaining why we're all here. There's a famous quote from Carl Sagan that says, "We are all stardust," which is true. All humans are made out of stardust. The elements that compose our body, except for the hydrogen atoms and a few helium atoms, all came from the interiors of giant stars, or were created during the cataclysmic explosion of those giant stars. Literally, every little particle that makes you up was once inside of a star. So helium is significant. This is an idea we keep seeing. We keep seeing a significant portion of helium. One thing that will soon become obvious is that the proportion of helium has to do with fusion itself, but also with the Big Bang. So you have to be careful when you think about helium. Hydrogen, clean cut, came from the Big Bang. That's how the universe started. Helium is the only other element that was created in the Big Bang. And I know I'm jumping way ahead, but I don't want to hide this information. Now, the thing is that helium also is the most readily produced element from fusion. Fusion being this, source of energy, this process that occurs inside stars. So it comes from two places, stars and the Big Bang. Carbon produced from fusion and just a tiny bit in the sun. That amount will gradually go up as the sun reaches its final life stages, but never get that large. Nitrogen, oxygen, these are just trace amounts that were left over from previous generations of stars, and our sun will never produce them with fusion. They're too heavy, and our sun is too small of a star to ever produce these heavier elements through fusion. Same goes for neon, magnesium, silicon, sulfur, and iron, which are all solar products, direct solar products, but are only created inside of the cores of the biggest stars, which are relatively rare. Our sun, which we'll talk about much more in chapter 17, is a very typical star. It's just your average garden variety star, nothing special about it. If we compare the amount of hydrogen, helium, and so on to other nearby stars, we got some names of stars in, that of course have their own, solar systems, their own planets. Almost every star does, although some have not been confirmed, of local stars at least. Alpha Draco, Omega Pegasus, Vega. Vega's a well-known bright star in the sky. So these other ones, the first two are not. Theta Leo. So all of the names, by the way, often have the name of the constellation second. So if you look at this name, Alpha Draco, that means it's in the Draco constellation, which is not a super well-known constellation of the 88 constellations. Alpha means that it's the brightest star in that constellation. Omega Pegasus means that it's the dimmest star, or at least the, whatever letter omega is in the Greek alphabet, probably around 23 or 22. So it's a very dim star in the Pegasus constellation. Vega is an exception because Vega is such a bright visible star that it has a name separate from its constellation. You only see that with a handful of the brightest stars that had historical names those names have been kept, but they don't meet that same convention. Theta Leo, however, does. Leo constellation. Theta is just a letter in the Greek alphabet, kind of in the middle. So it's sort of a fairly dim star, but not the dimmest. And yeah, and I have to check if the idea is that Omega is literally the dimmest, but then what does that mean? There's many more stars, right, as you get dimmer and dimmer. So it's probably just whatever letter that is. And I don't know if it starts over after that, if you have how they name stars that are even dimmer than once you run out of letters of the Greek alphabet. Anyway, that's neither here nor there. But if you look at the hydrogen, it's pretty comparable, although the amounts are greater for these other stars in terms of the amount of hydrogen, and the helium is all a bit lower. And I was thinking about kind of what that was telling us, and it seems to be about the life stages of these stars, which is something we'll talk about in depth, and we'll get a decent intuition of talking about life stages of the stars and what they're up to. And you can really think about what their fuel source is in terms of how old the star is, if you know how big the star was when it was born. And big stars live short, high energy lives. Smaller stars live much longer, stable, relatively lower energy lives. Again, our star is kind of in the middle. It has a lifespan of about 10 billion years, which means that at about the current 4.5 billion, the sun is just under halfway through its lifespan. When it dies, it will stop with fusion. It will run out of elements that it's able to fuse, and that will cause a series of events that will eventually leave a white dwarf behind, which is a corpse, if you will, but also a remnant of a star. At that point, there will be no star in the traditional sense, although white dwarfs sometimes are called stars. There's no fusion, so they don't, they're not a fusion producing body in the solar system. They'll just be a white dwarf. And that you would say that at that point, the solar system is essentially dead. Certainly, it would not be able to sustain life anymore. But that's what's happened here with these different amounts of helium and hydrogen, is kind of how much of that fuel has been used up. There's not a kind of clear story to tell, nor would it be totally appropriate or make sense to do it at this point. We'll have opportunities to talk about comparisons between stars and something called the HR diagram, which is this wonderfully condensed but also clear summary about almost everything you need to know about stars. It's often compared to the periodic table for chemistry. It just sums everything up that we need to know about stars in one figure. But carbon amounts also vary. Notice that they're like greater for Alpha Draco. That's probably because that star is at a phase where it's producing carbon. So it's been and has been producing carbon for some time. So it's made extra carbon. And then a comparison in this would be, instead of a kind of like spatial comparison, right, to other stars that are spaced out and far away. Instead of comparison over time, a temporal comparison, how does this composition of the sun compare to how everything started in the solar system, right? Because we've talked about this, earliest atmosphere for the planets quite a bit. So I'm leveraging that familiarity. And we said that it was shared by all the planets, even the gas giants. It didn't last for any of the terrestrial planets, but became the building blocks of all the gas giants. And the reason that it was so universally shared was because it was the composition of the protoplanetary disk, the disk that formed everything, that started from just a big nebula, a cloud of dust that collapsed under gravity. Okay. Well, the composition of that primordial solar system, or the solar system, was less, or wrong word, more hydrogen. There's more hydrogen than there is today. Well, at least in the sun. Now, that right there, drives home the point that the sun has been doing something with that hydrogen. And I think I almost can't resist the temptation to talk about fusion, right? Although, honestly, we'll get more into it in the next chapter. But that's what's been happening, is that this 94.2 went down to 92 because the sun's been using it up. It has been literally doing transmutation of elements. I love that that's the official term, because that also is the term that gets used in alchemy, right? Which was a pseudoscience, not a real science, but an honest attempt at one. With trying to turn lead into gold. Well, stars actually do things like that. They change the elemental properties. They change one element into another. It just turns out that the conditions to do that were not attainable by just a fireplace and a cauldron and something like that. You have to have some pretty intense pressures and temperatures. And the helium has gone up. See, helium before the sun came to life was 5.7, right? And so in the early solar system, now it's up to 7.8 inside the sun, because it's been made. All right. And in comparison to Jupiter, we see that same sort of trend, that the sun has more helium and hydrogen than Jupiter. So Jupiter captured more of that primordial amount of hydrogen and helium, and it hasn't changed much because there's no fusion in Jupiter. Jupiter is not a sun, nor is it even close to having been one. It doesn't change hydrogen into helium. It might be super dense and hot at its core. Absolutely, it's a big planet, but not close to high enough temperature to actually create helium. Now, if you look at, and so this is kind of interesting, if you look at the kind of the things that we've talked about so much throughout the solar system when it comes to planets, like methane, ethane, ammonia, and CO2, and even diatomic oxygen, those are all molecules. And here we're being asked, why are there hardly any molecules in the sun? So the sun has everything in the atomic state, no molecules. We're not going to find CO2 in the sun, even at its surface, let alone its interior. Why? Go ahead and tell me in chat. All right. I got 2 votes for 2. Too hot? You're absolutely correct. It is way too hot. There's plenty of energy for dissociation to occur. We talked about that with Venus, right? And just because it's so hot within the atmosphere of Venus that H2O dissociates. Well, even a much stronger bond than that would dissociate in the sun, okay? This one's showing the number of hydrogens for every one atom. So there's going to be 12 hydrogen atoms for every one helium atom, 4,600 hydrogen atoms for every one carbon atom, and so on. So this is a way to talk about abundance. And then if you look at the actual mass, so 73.4% comes from the hydrogen. So because yes, in terms of counting atoms, it's the majority of them. But remember that every one helium atom is 4 times heavier than a single hydrogen atom. So it counts 4 times as much for a mass calculation. So if you think that percent of atoms is going to give you the percentage of the mass, well, be careful, it won't. And it's simply because, right, atomic mass of hydrogen, just 1 proton, thus 1. Helium, 2 protons and 2 neutrons, thus an atomic mass of 4. So every atom of helium is 4 times heavier. And same logic would apply to these other heavier elements as well. So we got 25% of the mass actually coming from the helium, even though it only makes up 7.8% of the atoms, which if you think about it, I'm sure makes sense. Right? There you go. So good summary there. All right. Skipping through some of this. All right. So now on to the solar structure. What are its properties? All right. Talked about planets' properties, characteristics, we usually call them. It has a radius of 700,000 kilometers. All right. So that is way bigger than anything we talked about. No surprise, right? And so, I mean, it's a couple quick comparisons. All right. So we got, for Earth, we have 6,370 kilometers. Okay. So that means that the sun has a radius that's approximately 100 times greater than the radius of Earth. All right. Jupiter, if you remember, had about 11 times the radius of Earth. But the sun then, would still be over 10 times bigger than Jupiter. And just on radius, because remember, radius doesn't tell you volume. To get volume, you have to cube the proportionalities like the ones I was just saying. Case in point, the mass of the sun is approximately 2 times 10 to the 30 kilograms. It with 3 significant figures is actually 1.99, so it's really close to 2. And that's about 330,000 times greater than the mass of Earth. So we have a incredible amount of mass, right, concentrated in the sun. We take 330,000 Earths to make one sun in terms of mass. The density is relatively low because even though the core is quite dense, the outer layers just being formed of hydrogen and compacted under the intense gravity associated with such a big mass, still can only, compact so much. And they are also in a balance because there's a lot of outward energy. We'll learn that stars are all about not tearing themselves apart from the inside because of too much outward flux and not collapsing from the influence of gravity. So it's that balance. You push out due to heat, gravity pushes in, and when the two are in equilibrium, you have a stable situation. And so this density kind of shows that stable situation makes stars not that dense. Sun is an example. And it's like they're basically like a gas giant, very comparable. More because of averages than saying that every layer is identical. That would be false. If you look at the density of the core of the sun, you're going to get very different values than you'd get from the core of a gas giant. But as an average, the densities are comparable. Temperature, surface temperature of the sun. We actually know this back from chapter 5. 5,800 Kelvin. I'll put the unit over here so it's easier to read. As we usually do, the units are in kelvins. Sometimes we see things in Celsius, even occasionally in Fahrenheit. So, some amount of conversion might be necessary, but usually it'd be made clear. And just remember, Kelvin's the absolute temperature scale, and definitely the one we care about when we talk about stars. Okay? And this is going to tell us the peak wavelength has to do with that, the visible spectrum that comes from the sun, and the most common color photon that's created, and so on. And that was, if you recall, the black body radiation curve and Wien's law is how this temperature is directly related to the color as well as the intensity of the light that comes from the sun. So when we say that its temperature is 5,800 Kelvin, what part are we talking about? Okay, what part of the sun has that temperature? What do you think? The interior? Is it referring to what goes on the inside, and then maybe it glows out? The photosphere, which is the part that's kind of plays the role of the ground. The atmosphere, which is above the photosphere. Some sort of average? Is it just averaging across the entire sun? What do you think? And cool. So I had Alara said 2, Isabel said 2, Nicholas potentially 3. Yeah. Cool. That's what I would expect in terms of answers. Thank you for letting me know. And the reason is because I think it's reasonable to say, oh, it can't be the interior, right? We can't see the interior. And averaging seems strange. We haven't seen that sort of calculation, why would we do that? So it comes down to what are we, what are we talking about when we talk about temperature? What is it? It's going to be, and I did just talk about its importance to color, right? So it's the part we see. So therefore, what we see is called the photosphere. So this image here shows the photosphere. But what about the atmosphere? Because that one is tempting, right? Is that because isn't the atmosphere above it? The light has to pass through it. What's the effect? Well, the atmosphere is not terribly dense, the sun's atmosphere. It's also strangely much, much hotter, which is no one expects. But it turns out to make decent sense. Although I remember being confused by it for quite some time. But hopefully I can explain it to you all, so that you do not have to be confused about it for quite some time. But the atmosphere is most famous because it's only visible, or rather its claim to fame is that it's only visible during solar eclipses. So when people talk about seeing the corona during a total solar eclipse, that's what they're seeing is the sun's atmosphere. That's, at least that part of it is the upper part of the atmosphere is called the corona. And that's also the hottest part. But it's way too dim normally to see, but you actually see it glowing during a total solar eclipse. Okay. So otherwise, it's invisible. It's washed out by the intense light coming from the photosphere. All right, let's look at our layers of the sun. I sort of said that, we'd be doing this more in chapter 16, but here, this is just kind of a quick introduction to it. If we start at the core, that's the very center of the sun. That's where the fusion happens, okay, where fusion takes place. It's a high energy gamma rays are produced if we're thinking about a path of light, right? So there's the production of light. That light, that's, we think that is really kind of perhaps the thing we care about most about the sun. It produces light, the light we need to live, the light plants need for photosynthesis. All right, but gamma rays would be no good as a source of light for us, right? Way too dangerous, too high energy. Next, as we move out from the core towards the surface, is a region called the radiative zone, shown here with a bunch of wavy lines passing through it. The core was this more green, sort of, bluish region at the very center, and the source of the wavy lines. That is where the light is produced. The gamma rays are produced as a byproduct of fusion. That's where they're coming from, okay? It's part of the E equals mc squared part of fusion, the fact that we're turning matter into light. Because when people talk about turning matter into energy, pure energy, well, it can take more than one form, and that's often overlooked. But one form of pure energy that has no matter is light, because light doesn't have mass. But anyway, the radiative zone is always described as this, part of the sun where there's no, it's not the, essentially it's always, I always thought of it as just not the convection zone, which we'll talk about next. And we have here that the energy travels as electromagnetic radiation outwards from the core. So it's just passing through the radiative zone, which the name implies. It's a zone of the sun where very high energy photons are converted to many lower energy photons. So the gamma rays get changed into X-rays, which are still plenty high, but much lower than the gammas. Probably some ultraviolet, even some lower energies, since it is a random process. The best way to think about the radiative zone, although that's a good description of what's going on, I don't think it really evokes an image in the mind. But if you think about it as being like glass, essentially, this is like a big layer of glass, not made out of, typical components of glass that we think of, on Earth, but really having similar properties. So it's just a big, super high pressure, super high temperature, compressed, ionic gas, plasma, but behaving just like glass. So it's just this big sheet of glass in the shape of a sphere that surrounds the core of the sun. At some point, the pressure becomes light enough, goes down enough that solid state, transitions to a liquid state. And that outer layer of the interior is called the convection zone, because now the plasma that forms the entire sun is behaving like a liquid. Here, the energy travels as convection cells from the interior to the surface. So in terms of heat transfer, the names are really good, because literally the radiative zone is all about radiation. That's literally how the heat, energy measured in joules, is moving from point A to point B. Okay, just passing through that transparent material. But once you get to the convection zone, there's very little, transport by radiation, just like, you don't have a lot of light penetrating the ocean beyond a few meters, right? It's true of any fluid. Fluids are too dense for too much transparency. And they don't have those properties that are, kind of like, why is glass transparent, right? Because it's unique structure, and it's only transparent to visible light, and some other wavelengths. Well, you have to have, particular crystalline solid to offer some sort of transparency. You can't have a random mix of molecules all bouncing around and preventing the pathway of light. And that's certainly the case in the convection zone. So the only way the heat can move is through the bulk movement of fluids. Hot plasma rising, expanding, cooling, and sinking back down, just to repeat the process over again. And that's what the convection zone is all about. Notice I've said the word plasma a lot. I've been doing that on purpose. That's the state of matter inside the sun. And it's sometimes like confusing to people, because they're always like, oh yeah, there's, solids, liquids, gases. And isn't there that one other state, like a plasma? How's it different? Well, the difference is so straightforward that I can't stress it enough. That the only difference between a gas and a plasma is that a plasma is a gas where all the electrons have been lost. It's called ionized. So plasma is simply an ionized gas. That's it. All right. Now, I did say that, the convection layer is a solid, right? But it's compacted into that glass-like structure, but it still started as an ionized gas. So I guess now it's an ionized solid. All right, so this is just showing those convection cells. We talked about convection cells when we talked about Jupiter, for example, if you recall, right? Called zones here, but also sometimes called cells. Okay. Here is another analogy that I gave when we talked about Jupiter, that I said, hey, convection happens in our, beneath our crust of the planet, also in the mantle, as well as in our atmosphere, right? So lots of examples. Happens in the sun too. Yep, that's true. And it will be next week for us too. All right, because that's when we're really going to get into what happens inside the sun. Our focus now is going to be turning to outside the sun, the surface, and for the rest of this lecture, it will stick outside the sun. So photosphere, surface of the sun, it's the part we can see. So when you look at the sun, don't look at it for too long, you see the photosphere. And that's its temperature, gives us the color. So I got a question for you. I touched on this, so maybe it'll be obvious, I don't know. We can't see material beyond the photosphere because of the density of the material there. So it's anything above the photosphere, anything that collectively would form the layers of the sun's atmosphere. But the density of that material is what? Too high to allow the light to escape, too low to allow the light to escape, too high to produce much light, or too low to produce much light. What is it? Just, yeah. Good one for straightforward reasoning. Okay, I got a vote for 1 and 3. Okay, well, thank you, Nicholas, Isabel, Fior, and Alara. I feel awkward about calling it straightforward reasoning, but oh, okay. Oh wow. I thought it was okay. Now I just feel doubly awkward because I didn't think, wait, too high? Oh, well, I should have read the question. This whole time I read the question as we can't see the material above. And if you heard me talking about it, that's the way I was interpreting it. So I totally misread it. Can't see the material below. Yep. And exactly. No light escapes from those lower levels. So yeah, you got it. Everybody that said 1 got it. Good. Good. It's the light is trapped in there. It's the same reason you can't you don't see the light glowing from inside of a rock. You just see, the surface. The way I often think about it is if you were to zoom in to the molecular or atomic scale, and you'd see a bunch of domino effect chain reactions. You'd see light being produced by one atom, traveling the distance, to the next atom, getting absorbed by it, repeating over and over again until it makes its way to the surface. That, by the way, is conduction. That's how heat moves through solids. And there's conduction in liquids as well. It's just liquids can take advantage of convection, which is speedier, faster than conduction when you deal with liquids. So, but every time the same thing involved, is a result is that light never makes it to the surface because it just got absorbed by another atom and then re-emitted until it finally hits the surface, whatever, either that's the surface of a, transparent gas like the air, that we're in, or if you're in a true vacuum, then that's kind of a clean cut case as well. So then the light comes right out. So cool. You definitely got it. All right. So the whole time I was thinking about, why we can't see the atmosphere, which is a whole, separate discussion, and one that we'll touch on. Okay. Let's see, we're almost at break time. I just want to say, yeah. Okay. So yikes, there it is. Okay. So in terms of granulation okay, that's fine. So yeah, we'll pick up on some surface features after the break because we're moving on to kind of a separate topic here. We're going to be talking about the these things here, this granulation. You can see it in the images, right? So like, this one here, if we zoom in on it, we see these, what are, kind of referred to as granules when they talk about the surface of the sun. All of these obvious, like, separate features that look kind of hairy, right? So what are they? What are those? What do they represent? And that's going to be our next topic. And we obviously a concept question showing it as well. And talking about how they might relate to convection zones. So we'll get into that after a 5-minute break. So let's plan on being back at 11:27. So 11:27. All right, so continuing with our discussion of the sun and the photosphere. So focusing right now on the surface of the sun, we're kind of talking about the surface features, like when we talked about the surface features of planets, But of course, here it's just the surface of this ball of gas, this ionized gas. All right, so we have these granulation patterns. Seen them in different images of the sun. There's a zoomed in image here. The window, kind of the diagram overlaid on top of the photograph, is showing us that these granules correspond to apparently a few convection zones located underneath. That's a big hint in terms of the answer here. And we're just asked to identify what they are. And specifically the dark edges. Are the dark edges the hot material that's rising, the hotter material that's sinking, the cooler material that's sinking, or the cooler material the cooler material that's rising, which is 3, and then 4 is sinking cooler material. So which is it? Okay. So yeah, because cooler stuff will sink. But it seems like that those of you that answered went right for the cooler. That grabbed your attention. And that's good because we did briefly see that with the gas giants, and it makes sense that the cooler is darker, right? So the cooler gases are going to show up as darker. So that was a good intuition. So here's our answer. So it's that dark because it's cool, and since it's cool, it's sinking. This is the way to think about it. Okay, so that the whole surface is showing really kind of fairly direct evidence of all of that convection. Every time we see, all those granules, we're seeing this constant process of upwelling, cooling, and sinking. And therefore, I'm sure you would imagine that if you look at a video, right, a time lapse showing the granules over, many hours, but sped up, they're always moving around. They're changing shape, they're disappearing, new ones are forming, because it's just a constant dynamic process. They're obviously not stable and just going to always stay in place. Yeah. So gas at the edges of the granules is sinking back down. So it's just like this big, like kind of, like I said, like an upwelling of hot gas, and it sort of like flows off the edges and then sinks back down. So a big plume of hot gas coming up. Almost like like in a lava lamp, right? That big glob coming up, and then sort of like imagine then if it could break apart and sort of like sink back down. In that case, they're forced to stay together, which makes sort of an odd pattern. But in a fluid, they're more free to move around. All right, so looking at the wavelengths, the light that's produced by the granules. So here, gas at the edges of the granules are sinking back into the sun. Compared to the gas that was not moving, this gas will show wavelengths or show blank wavelengths in its spectrum. So what they're talking about here is the Doppler effect. Now, we already said that just the sheer color, right? The dark versus light tells us something about the temperature, but we can confirm that. We can really confirm it, right? Validate the idea with movement, and we can get movement from the Doppler effect. So, do you remember your rules for the Doppler effect? So again, it's asking about the gas that is sinking back into the sun. So the dark regions, will it show, compared to that same gas in the laboratory at rest, will it show a longer wavelength, a shorter wavelength, the same? Is it just no? Am I wrong? Is it not a way to validate it and it's just completely different? All right, so I got 2, 2, 2, 2, shorter for the gas that's sinking back down. All right. Well, Fiore, you came in at the end. So you got all right. All right. Yeah. So because it's moving away. And anything that's moving away from the observer it's called redshift. And what the redshift refers to is that it's redder than it would be otherwise because it's longer wavelength. So any source of light moving away from you has longer wavelengths than if it was at rest. Okay, so that's a good summary there of what the granules are all about and a good review of the Doppler effect. Okay, so now moving on to the chromosphere, which is above the photosphere. So this is really getting into the solar atmosphere. When we go up to that next layer, it is a thin, hot region that is glowing red from hydrogen alpha. It's largely invisible except during eclipses. So you can see some of this effect happening in the chromosphere. Hydrogen alpha. What's it referring to? Let's see if it explains it. Otherwise, I'll have to look into that. An image taken from a space probe, by the way, the one from the side. This other one is a solar eclipse image, but this appears to be a solar eclipse that was probably taken from the International Space Station rather than from Earth because you don't see the atmosphere around it. So looking at the photosphere, we see a certain type of spectrum. Okay. Yep. So this one we can definitely answer. Although I'm still I honestly don't know what they mean by hydrogen alpha. I feel like they don't mean alpha particles because that's just the nucleus of a helium atom. Alpha. What state? Is it it's got to be some sort of excited state of hydrogen, which would probably make sense. Unless it's just the emissions of atomic hydrogen. But well, I don't want to say too much because I might give away this one. So okay, don't worry about it for now. I'll have plenty of time to confirm what hydrogen alpha is. It's obviously just some sort of state of hydrogen. But here, basic question about spectrum and another great review. A lot of kind of chapter 5 review stuff here. So looking at the photosphere, we see what type of spectrum, and your options are absorption, continuous, or emission. And then looking at the chromosphere, the lower atmosphere that we just introduced, we see what other type of spectrum. So feel like you got this one? Let's see. Okay. So I got votes for 4 and 3. Okay. So interesting. So they gave 2, not 3. The photosphere is we're seeing the light come out. It's associated with, it can't be right, because that's the whole black body. There's absorption. I don't want to waste time on this, but like, I'm guessing it's just a typo. There is a big idea with stars that we were able to figure out what molecules exist but that's the upper atmospheres. And that's absorption because but that would not be the photosphere. Yes, that's not where it's still too hot to have a significant number of molecules. So no, there is not absorption in the photosphere. There's not. Now, this is definitely, yeah, this is definitely a typo. I would imagine the arrow is just put in the wrong spot. So the correct answer is 3. It's a continuous spectrum. The photosphere is a black body, and it's emitting that continuous spectrum just like any other solid object. But the emission, the reason I like the question, although I had not noticed the typo, is what's happening in the chromosphere. So in the chromosphere, we're seeing the emission spectrum. We're seeing it glow. We're seeing a hot gas, because remember, absorption occurs in a cold gas. And so an absorption spectra is, light passing through a cold gas, and then you look at the gas, what's missing, what got, absorbed by that cold gas. And you might, if you can look, you might be able to still find an absorption spectrum hidden, within those dark bands, but it's just so much weaker that you need a very different type of device, right? Like a really different calibration to see it, because it's like very, very dim. But the primary thing that's happening in the chromosphere is emission. It's a very hot gas instead of a cold one. And so it's energetically releasing light that came to it from the, hot surface of the sun just below it. Okay, so then, and I haven't really been referring to these diagrams, so I will for the first time. I wasn't, because I was thinking, okay, well, we're talking about the interior layers later, but let's quickly take a look, okay? So we've got, I'm just going to focus on temperature, again, because density is going to be a discussion for when we talk about what's going on inside of the sun. But for a quick review of temperature, when we started at the core, we were at 10 million Kelvin. We'll get back to that number. It's a special number for fusion. Then everything got gradually, I know it's crazy hot, but then everything got gradually cooler through the rest of the core, and then the yellow being the radiative zone, and then this light blue is the convection zone. So by the time we reached the photosphere, we were right in this region here, between 10 to the 4 and 10 to the 3 Kelvin. And of course, that's between 1,000 and 10,000 Kelvin. And that means that this little minimum point right here is the characteristic 5,800. Okay, so the temperature of the photosphere, which sets the color of the sun, which is all the more reason we know it's a continuous spectrum, and that last answer was a typo. Now, as we've gone into the chromosphere, this super hot gas that's emitting light due to a hydrogen reaction, the temperature is going back up. All right, so we actually counterintuitively hit a minimum at the quote unquote surface, and in the atmosphere, the temperature is climbing. The beauty of this is that with enough knowledge about how, I guess, stars and planets work, it actually starts to become not counterintuitive, but I called it counterintuitive because I certainly, remember myself thinking that. And what I'll point out is that in the interest of time, and still there's a lot of this content takes a while, but we didn't really look at the layers of atmospheres for any of the planets, not for the gas planets, not for the terrestrial planets. And we talked about their composition a lot, but we never talked about their layers and about the temperatures of the layers. So I believe there's a couple figures in the book if you are interested in that. But what I will say, in that what you see for, and we'll take it back to Earth, right? Because that's the easiest to think about. If you were to look at the temperatures of the atmosphere on Earth, you would find that they first go down, which is what we expect, because we think that, if you go up to high elevation, as the air gets thinner, it gets really cold. And that's true, okay? But then as you get to the very edge of the atmosphere and you approach outer space, the temperature of the atmosphere shoots back up and then goes way beyond the troposphere, which is the lowest level of the atmosphere, where we breathe, right? And that's because of absorption of high energy photons. Basically, it starts going up because of absorption of UV, and then it goes way up because of absorption of X-rays. So you have super hot atmosphere at about 150 kilometers above Earth's surface. That's in the, approaching 1,000 degrees Fahrenheit. But that seems weird, right? Unless you're like, oh, is that why like spaceships burn up when they re-enter atmosphere? No, that's because they're going really, really fast. And as soon as there's any friction, that energy has to go somewhere. Because even though it's super high temperature, it's not hot. Because heat is a combination of temperature and density. And the upper atmosphere is incredibly low density because we're approaching space. So you have really hot molecules in that they're super energetic, having absorbed X-rays, but there's not many of them. So if you were in that upper atmosphere, you wouldn't feel the warmth. You would feel freezing cold. If you had a breathing mask on, so you wouldn't have to worry about suffocating, it would feel freezing cold, despite the fact that the temperature reading is really high. So that's the thing about temperature. Temperature just refers to the energy of molecules. It does not refer to heat. And so that's why almost every atmosphere tends to have really high temperatures at the very edge because of absorption of high energy photons. Okay, so we're kind of seeing the same trend with the sun. But of course, the sun is the source of the high energy photons. So maybe that explanation isn't quite as cut and dried, but at least it is showing us that same trend. All right, and I'll kind of get back to what I was hinting at about questioning why it goes up. But anyway, we have the transition zone, and that's the temperatures jumping back up into approaching 1,000,000 Kelvin. Okay, not quite within the transition zone itself, this narrow 60-mile region. It shoots way up, and then it hits the corona, where it stays at about 1,000,000 Kelvin. So it's at that 10 to the 6 level. Can't draw it straight. And it's above 10 to the 6, but it's a logarithmic scale, so it's probably only about 2,000,000 Kelvin, right? Because that's the way these types of scales work. They're powers of 10. So somewhere in that range, 2-3 million Kelvin, but single digits in the millions, as opposed to the 10 million, which was the core temperature. So it's cooler than the core, but it's still incredibly hot in terms of temperature, and way hotter than the surprisingly hot upper atmosphere of terrestrial planets. And that's strange, right? But again, it is very, very low density. So we have super hot gas, but not a lot of heat contained there. All right, and it goes way out. The corona, that's the name of this final level of the atmosphere, stretches all the way out past Saturn. Okay, and it's just this huge region, although I mean people really just think of it kind of going to about Venus, really. But technically it does go all the way out, composed of strongly ionized atoms producing strange emission spectra. And that sort of that region of how far it goes is important for thinking about the overall electromagnetic interaction that the sun creates within the solar system. But for most purposes, we don't care that it goes out that far. In fact, we usually think about it as just being, just a little bit above the surface. Here we see an image in X-rays, because that's what the corona is emitting. It doesn't emit any, it does emit some, but it doesn't emit much visible light. It primarily emits X-rays. Some animations you can look at if you want to follow the links. Okay, within that corona, the solar wind is flowing outwards and beyond. The solar wind does extend well beyond the gas giants, way out into the Kuiper Belt. And it is a constant outflow of high energy particles, protons, and electrons. So it's not light. Obviously, light flows outwards into space as well, but the solar wind is a separate phenomenon. Unlike light, protons and electrons have mass. And unlike light, they can interact with magnetic fields. Light doesn't. Light may be electromagnetic itself, but it does not interact with electric and magnetic fields. But solar wind does. Okay, so talking about the importance of the sun and the main ideas of this chapter, this kind of return to this a question is serving the purpose as of the sort of the sections of the lecture. And a big thing that we care about with the sun is this this solar weather, the thing that what's coming off from it. So the solar wind and the corona and the fact that they extend so far into the solar system means that the sun has a effect well beyond its immediate boundaries. Okay, so now we'll return to the surface for a while to talk about sunspots. This is a fascinating aspect of the sun because it will get into the cycle of sunspots, which has to do with the sun's magnetic field, and also what the sunspot is by definition. What are we actually seeing when we see a sunspot? So sunspots are dark spots moving across the surface of the sun. These are not the same as the dark edges of the granules. These are much larger dark regions that are going to, cover what would have been a whole patch of granules. They do vary in size. All right. This image obviously is taken in such a way that we can't see the convection cells as clearly, just because of how it's imaging the sunspots. I don't know if it's in the visible spectrum. It may not be, maybe artificially colored. But you could follow the link to check out the source of the image. So why do the sunspots appear dark? Well, I won't wait for an answer or check, but look at your options here and think about what we're talking about the granules and the dark edges of them, because that's a hint. So they're not giving off light. So I guess they're just the absence of light. The sun's light is being absorbed by a magnetic field at the location of the sunspot. An object is passing in front of the sun, maybe the shadow of something. It's all the spaceships. Light is being absorbed in an outer layer of the sun. So there's some sort of absorption process that just, is either re-emitting in a different direction or just the random re-emission doesn't show up. It's too faint. Or they are cooler than the surrounding region and showing up darker because they're cooler. Well, it's just the cooler region. So it's like the simplest explanation. And that's the same reason that the dark edges of the granules were dark, because they're cooler. They cooled, and they're also sinking, right? But they're sinking because they're cooler. So it's the exact same logic that the cooler spots show up as darker. So talking about black body radiation, this graph illustrates the black body curves for a normal region of the sun's photosphere and a sunspot. Which curve is from the sunspot? Is it going to be the curve with a peak that's right around like 550 nanometers and has a very large amplitude? Or is it going to be the curve with a peak that's in the infrared and has a much lower amplitude? Well, I bet I won't check at the moment, but give you a moment to make sure you feel confident about your answer. Put it in the chat if you want to, please. And it's no answer at all. Obviously I forgot. It's this one right here. That's the sunspot curve. That's why it's dark, right? Because look where the peak is. The most likely photon that's being created by the sunspot, and again, this is just yet again confirming, right? With it, their own slides are confirming the typo. So it's not just me. If you want confirmation that clearly this is a continuous spectrum discussion when we talk about the photosphere. But anyway, the sunspots, if we could see infrared and not visible light, they'd appear brighter, right? If our eyes were calibrated in such a way that infrared was the light that we saw, the sunspots would be the bright part and the rest would be dim. But we can't see infrared, which is why they look dim, because the peak is just outside of our visible range. Now, of course, the lower intensity, matters, but the sensor matters more, right? If our eyes just weren't able to pick up this high intensity light, it wouldn't matter how bright it is to some extent. I guess it would still matter in terms of the tail, right? So the fact that at that wavelength, the tail is still brighter, I guess would mean that it would, unless you had like a way to like filter it out, I guess it still actually would appear brighter, even though it's not the peak, just because the whole curve is so much larger. We talked about that briefly. It's a cool thing about the black body curves, right? I think it's really cool that we can just relate temperature to color, right? If we know color, we know temperature. But then the fact that these curves vary so much in how like large they are by just changing the temperature, a fairly small amount, right? Just going from probably like 5,800 Kelvin to maybe 3,000 Kelvin, right? So, we're not going to like, absolute zero or anywhere close to it, right? We just got a little bit cooler relatively, still hot enough to melt metals. But the curve's so much smaller, the light is so much less intense. And that's because there is that fourth power relationship, which is very uncommon, right? You see square relationships, cubic relationships, but the intensity, which is like the size of the curve, is proportional to the temperature raised to the fourth power, which is why that green curve is so much bigger. All right. So seeing the sunspots, they move around the surface. We'll skip over this one. One thing that the sunspots have allowed researchers to do is record the differential rotation of the surface of the sun. So the surface moves faster at the equator and slower at the poles. This isn't unlike the differential rotation that we saw for gas giants, although we're not seeing bands of opposite directions, but that was pretty unique to Jupiter. But there was still differential rotation for all of the Jovian planets, and there's a similar phenomenon going on with the sun as well, although namely it's just that you get slower as you move away from the equator. And so if these images represent equal changes in time, and we can clearly see that the equatorial sunspot is covering a much greater translational distance than the higher latitude sunspot. Now, the cycle that I mentioned. So the solar cycle tells us how many sunspots there are, or rather, historically, the solar cycle was discovered by counting sunspots and noticing that they would peak, the number of them would increase if you observe the sun, over consecutive days and months and years, and then eventually reach some peak amount where there's a bunch of sunspots all over the sun, and then the number would gradually decline until there was almost none. The sun would almost be completely blemish-free with no sunspots, and that cycle just repeats over and over again. And we can see, since the kind of the advent of high quality recording in 1800, for 2 centuries since, a cycle that repeats over and over again, okay, and can even be extended back 400 years on less rigorous methods. As we go past, further back in history from 1750, there are plenty of observations, but the methods were not as detailed. Despite that, there appears to be consensus and consistent with the methods used from the 1600 to 1750 that there was a region or an era about 50 years called here the Maunder minimum, where the peaks of that sunspot cycle were just tiny. There never were that many sunspots, although there were minimums reached at regular intervals. So what this shows us is that there's a pretty well-defined pattern in terms of minimums being really evenly spaced. But the actual values of the maxes, the max number of sunspots, and this is literally just counting them, are evenly spaced in time, but the max number varies. And it seems to vary somewhat randomly or have a more complex pattern that extends over hundreds of years. So and I thought they'd at least give us the value here, so I'll tell you. You can look at it, but it's not terribly easy to find. But maybe I'll show you one that we can read off. So let's find a minimum that coincides with a nice number of years. Doesn't exactly hit 1975, pretty close to 25. So if you look at the minimum here, so where is the next minimum? So then we have this. These are all steps of 5 years. So this is 30, 40, 45, 50. No, let's see. So 25, if that's 30, then that one would be 35. Yeah, that would be 40. That would be 45. And then this next thicker line would be 50, which is the next edge of the cell. And so if we see all those steps are 5s, I know this one is a little bit off, but anyway, then we look and we see that the cycle to go from minimum to minimum is, it looks like it's maybe less than 10 years, but remember that first minimum was before 1925, and the actual value, which you could read off more accurately, is 13 and a half years. So the sunspot cycle is every 13 and a half Earth years, and that is pretty reliable. That yes, there is some variation, but that average is, works out really nicely. And we can even see, right, as we go, through time, that although some things vary, the actual minimums hit every 13 and a half years. And it's the magnetic field that drives that cycle. The sunspots are magnetic phenomenon. The cycle itself is driven by the magnetic field. The other solar phenomenon that we're going to talk about to wrap up today's lecture are all driven by the magnetic field. So I'm putting that all out there to stress the importance that the sun's magnetic field has a big effect on kind of the somewhat instability that is visible on the surface, right? These variations, these like big bursts of energy that come off. If you heard of like solar flares, right? You've seen these these points where a bunch of gas is just sort of like blown away from the surface of the sun. All of that is related to the magnetic field. So it's a defining manifestation on the surface. Okay, so we covered magnetism quite recently, so I'm going to skip over this. All right. We know that Earth has a magnetic field. We know that it comes from this dynamo effect. That's kind of the good way to call it. It's also, you could say, it operates like an electromagnet. So the magnetic field generated by a terrestrial planet's molten core follows the same principles as an electromagnet, often called the dynamo effect, like a motor being called a dynamo. Okay, right? We know it occurs in some moons. We were just talking about that. Okay. We know that it flips and that flip gets solidified in cooling lava from the mid-ocean ridges. So looking at the sun in UV light, right? And we can show, this is showing light from iron particles. So this is essentially showing the magnetic field. So we can see magnetic field lines when we look in this spectrum, because we can see the iron particles, the trace amounts of them that exist in the atmosphere of the sun. And iron is a fairly common element and have been created by previous generations of stars, kind of left over, coalesced, and don't need much. And that glowing iron is going to be glowing along field lines, so we can clearly see some magnetic field lines showing up in the UV spectrum from emission of iron. Okay, so we can reveal the magnetic field strength that way. In fact, the sun is viewed in many different spectra. So sometimes the surface is shown with a Dopplergram, which is just black and white, just to show motion. So instead of showing like red shift, blue shift, it just shows light for moving away from you and dark for moving towards you. So that's the scale here. And notice that there's an overall darkening on one side and light on the other. That's because of the rotation of the sun. And then the finer scale variation is because of the uprising, hot fluid and then the sinking cooler fluid. We can also have a totally different. So this one is not like any particular wavelength of light. This first Dopplergram. Neither is the magnetogram. The magnetogram is actually looking directly at magnetic field polarity and just turning it to shades of gray. So it's just creating a gray scale to represent polarity. So seeing a bunch of different magnetic poles with, north being black and south being white. Then we can get into like visible light, what it actually looks like, what it would look like to the human naked eye. Then looking at different all actual particular wavelengths. So here looking at X-rays, because we can tell from the wavelength here, this is measured in a unit called the angstrom, which is just 10 to the negative 10 meters. So just think of it as a tenth of a nanometer. And so these are just very short wavelength light. All right, for this one, Let's see. Oh no, it's not. This is longer actually. Sorry, they're all measured in angstroms. And he says, wait, actually, I was thinking, well, if you convert that to nanometers, then it would just become 17,000. And so yeah, so this is more like infrared. So this is like the infrared of the photosphere. This is a shorter wavelength within the photosphere and getting into. Let's see. So we get down to okay. So if the angstroms tend to the -10. So make sure I'm going in the right direction. So it wouldn't go to 170. We go to, because this is 450, and because then they get shorter. This is where we get into things that are too short to see at visible light. Okay. So then so this one is 10,000 Kelvin, upper photosphere, 6,000 Kelvin. So 6,000 Kelvin has, this one should be a peak that's right in the middle of the rainbow. Okay, so this is okay. So here's the conversion. 4,500, I know we're getting short on time here. We still got 10 minutes. So 4,500 of this unit, which you hadn't talked about before, but it's the angstrom. It shows up a lot. It's fine if you haven't seen it. It's just a multiple of meters. It's 10 to the -10 meters. So I'll just write that. So 10 to the -10 meters. And actually here, let me just write 1 angstrom then. So 1, 10, okay, and then to the -10 meters. And we know that a nanometer, put right here, so 1 nanometer, which is the way we usually talk about visible light, we talk about it as hundreds of nanometers, is 10 to the -9 meters. So visible light ranges between 300 nanometers to about 800 nanometers, roughly speaking. So all of these are given in angstroms, but it's convenient for me, and I think for you as well, to convert these over to nanometers. And if we do that, we just drop a 0. So this would be 1,700 nanometers. So not 1,700, but 700. Yeah, can't speak for some reason. Guess I'm going for more than 2 hours. So 170, there you go, right words came out, nanometers. So is that visible? No, it's shorter than visible. So that means that this represents it represents ultraviolet, which is interesting based off the temperature because it's 4,500 Kelvin photosphere. But whatever process is creating ultraviolet, which is creating 170 nanometers, isn't strictly black body radiation because it wouldn't correspond to that temperature. But I'm not sure what the exact mechanism is, but probably some sort of emission. But here, this is straightforward, middle of the rainbow, literally, right? Because that's the visible light. And it's I wanted to mention this. This is what kind of motivated me to clarify the values here, is that this right here is 4,500 angstroms. Well, that's 450 nanometers. So that's right in the middle of the visible spectrum. So 450 nanometers. So smack dab in the middle of the visible spectrum. And it's the most common photon that's produced from the sun. And assuming a 6,000 Kelvin photosphere, right? We had it listed as 5,800. That's a little bit more accurate. Maybe they're just rounding here. So what I love about this is it really clearly shows, actually better than in images I've seen before, what the peak wavelength really looks like. Because I always describe the sun as sort of a green-yellow color. And indeed it is, right? That's a green-yellow color. If the sun looks white because it's got just as much of the blue as the red, so the overall effect is white to the human eye. But if somehow we could only see the most common photon that's produced, it would look like this. So in a sense, our sun is a greenish yellow color in terms of its most probabilistic photon produced. So cool. And then all the other ones are just we're going to have a bunch of shorter wavelengths. Notice we go to back to shorter than visible because this is 160 nanometers. This one here is just 30.4 nanometers. So we're getting the X-rays at this point. So we got X-ray emissions. These ones are all coming from the corona, right? Well, the chromosphere in the case of these first X-rays, but then X-rays from the corona, X-rays from the corona, and then we have more X-rays from the corona, and so on. All right. Some of them would be some of these longer ones, maybe like the 300 here, would be ultraviolet instead of X-ray. But certainly the shortest ones, this 94 angstroms, that's completely in the X-ray region. Too short to be ultraviolet. And we know that some of the ultraviolet ones actually help us see the magnetic field lines, and we can see that here. We see field lines kind of showing up from some of these emissions. If we go back to just a diagram that is capturing the ideas that all of those accurate but complicated images were showing, the sun's magnetic field would look something like this as a process. Okay, so the sun's differential rotation causes the magnetic field lines to deform, twist, and kink. So what that means is that the sun's magnetic field is a total chaotic mess, and it's actually never really going to look like this, right? Because just the chances of it ever being, like lighting up even for a short time are just incredibly unlikely. But if it ever did, if it ever happened to kind of just like reach some perfect state just for, an Earth day or so, it wouldn't be long until the differential rotation started to pull the magnetic field lines being created by the movement. Because okay, where's the magnetic field being created in the case of the sun? Because that's the question, right? It's not being created in the core. It's being created in that convection layer and the upper levels of the convection layer. So since the magnetic field is being created in the part of the sun that is moving around and undergoing differential rotation, that means that the field is always changing and always getting disrupted. And so here, that's what we see, right? The faster moving equator is going to stretch out those field lines until they fold back over on themselves and create these disruptions in the magnetic field and the resulting releases of large amounts of energy. Right? And to finally get back to an idea that I actually presented a few slides back in quite a few minutes was that the sunspots, right? They're cool. And why are they cool? Right? And maybe you weren't wondering, but we established that they were cool. It's because the magnetic field is strongest at the location of a sunspot. So a sunspot essentially represents a region where the field lines are coming right up out of the surface and are particularly concentrated and strong at that point. So the field lines will be perpendicular to the surface, and that causes that region of gas to not be able to convect and thus just cool as it kind of sits idly until the field line moves on to somewhere else in a few Earth days, sometimes hours. Right. So if the leading sunspot is a north magnetic pole, what is the polarity of the trailing sunspot? There they go. North, south. Because what the pairs of sunspots represent, and we almost always see them in pairs, is they represent two poles. And that means that they represent a magnetic field that is looping up out of the chromosphere and back down into it. So this is like if we could see the magnetic field, and we kind of did, right, when we looked at the UV emission coming from the iron. Well, that's what it looks like. It's coming up and arcing and back down in. Doop, doop. And how do we know this for sure, besides just matching it to other models? We can actually measure it directly with a type of emission called the Zeeman effect, because it turns out that magnetic hydrogen, or hydrogen that in the presence of a strong magnetic field, emits a slightly different wavelength than hydrogen that's not in the presence of a strong magnetic field. I actually did this experiment when I was a student of physics at UC Berkeley. It's one of the experiments you had to do to recreate the original Zeeman effect results. And it's fascinating because it's a tiny difference, but with the right measurement technique, you can definitively find it. And it really shows what's called a splitting of the emission line. And it's a way to detect a magnetic field other than, some of the methods we mentioned, right? Like looking at the emission from iron. So it's just kind of summarizing it, say, okay, well, these are your energy levels of an electron in orbit around a proton. And so normally that you have just a number of, discrete energy levels. And when you introduce a strong magnetic field, every one of those energy levels splits into two, separate energy levels. So you have a splitting of each, and a fundamental quantum state is what they're called. But you have a splitting of each energy level, and those energy levels are the ones where if you bring energy in, the electron gets kicked up to the higher energy level. That's absorption. When the electron relaxes back down to the ground state or a lower energy, that's emission. And so now the electron can jump up to two different spots, right? The middle one usually is not does not remain available, but the two splits is where the electron will land. So we have the splitting when we look. So when we can see the emission happening, if we look for the right thing, that's emitting it, because it's not just hydrogen. It's actually any emission, but it's the easiest to detect of hydrogen because it's the simplest spectrum. If we look right inside that sunspot, we can absolutely confirm there's a magnetic field there. And this is really the historical confirmation. Modern techniques are, much more diverse, but this is the idea that it was all based off of. Okay. So we will finish it there. I just want to take a quick look at how many slides we have left in terms of what I want to give you a heads up on for Monday. Okay. So yeah, so we just have a few slides left. I'll plan on reviewing them. So you're not responsible to look at them yourself, because I do want to talk about solar weather, since I hinted at it a lot, but we're almost there. So the plan for Monday is to finish up the few slides in about 20 minutes and then take the quiz. So we won't take the quiz first thing, but instead take it, somewhere between 8:20 and 8:35. Well, sorry, that would be the morning class. For you guys, it's the 10:45, say. All right. Well, that's definitely a wrap for today. Using all the time. It's always, a long haul. Oh, I didn't think I forgot. Stop the recording. Ideally, I'd trim that off, but probably won't.